Good day. Now we are going to present Multivariable Calculus BEE 20303 by Ethan Zhong, Yem Sing Ro, Woonja Kwan from Group 9 Section 2. For this project, we select MATLAB as our primary computational tool. We specifically utilize the Symbolic Math Toolbox. We chose MATLAB because it allows us to perform symbolic integration, meaning we get exact algebraic answers like pi or fraction, rather than just decimal approximations. This was crucial for verifying the accuracy of our manual derivations. Throughout the project, we used MATLAB scripts to define our variables and run the integral to ensure our manual steps led to the correct final values.
Now let's begin to question 1. Good day, doctor. I'm Yem Sing Ro, number matrix AE240047. So I'm going to explain about question 1. So for question 1a, we are asked to calculate the double integral of the function 2xy squared minus 4x cubed over a rectangular region R. So since the boundaries are constant, with x range from 1 to 2 and y range from -1 to 1, the integration order is quite straightforward. I choose to integrate with the respect to y first, then by considering x as a constant. After substituting the limit and performing the final integration with respect to x, we get the final answer of -28. So now we're moving on to part B. The problem becomes slightly more complicated as we integrate the function x plus y over a region bounded by curve rather than the constant lines. Besides, the region is bounded below by the x-axis and above by the parabola y equals to x squared with a vertical boundary at x equals to 1 over 3. We set our inner limits for y from 0 to x squared and our outer limits for x from 0 to 1 over 3. After getting the inner integral and substituting y equals to x squared, we obtain a polynomial in terms of x. By integrating this from 0 to 1 over 3 and simplifying the result fraction, it gives us the final value of 17 over 4,860.
Hi, I'm Ethan, and now I'm going to talk about the software solution for the questions. So the question 1a, the first step we need to do is that we need to declare our variables, which is x and y, and then the second step is that we need to define our function. And for the calculation part, we need to integrate 2 times. So for the dy is int f1 comma y, which means it is respect to y, and then comma -1, which means the lower limit is -1, comma 1, and the 1 is the upper limit. So the outside, which is int, the first function, and then with respect to x, lower limit is 1 and the upper limit is 2. And then we display the answer, so the answer is -28. So for question 1b, we need to define the second equation. Since we already declared the variables in the first part, we don't need to declare it again in this part. So it is also the same where we integrate 2 times. So the first one is, so the inner part is with respect to y, and the outside part is with respect to x. And then the answer for this is 17 over 4,860, which is same as the manually calculated one.
Question 2. Moving to the manual calculation for question 2a, we were asked to evaluate the double integral of x squared y over the upper half of an annulus because the region is circular, bounded by the circles of radius 1 and radius 2. Cartesian coordinates are difficult to use. Instead, we converted to polar coordinates. We substitute x with r cos theta and y with r sin theta. Then, the area element dA become r dr d theta. We determine our limits based on the geometry. The radius goes from 1 to 2, and the angle goes from 0 to pi, representing the upper half plane. Our integral simplify to r power to the 4 cos square theta sin theta. Since the limits are constant, we separate the integral. The radial part results in 31 over 5, and the angular part results in 2 over 3. Multiplying this gives us our final answer of 62 over 15.
So for question 2, instead of declaring the variable x and y, we declare r and theta as our variable. So the reason for this is because we are calculating this question in polar coordinates instead of x and y. So the next step is that we need to define our equation, which is the x in polar coordinate and y in polar coordinate. So x is r cos theta and the y is r sin theta. And the next part is that we need to define the equation again for the calculation part. So we do the double integration. So the inner part is the respect to r. The lower limit is 1, the upper limit is 2, and the second part is with respect to theta, which is d theta. The lower limit is 0, the upper limit is pi. So then we just display the answer, and the answer for this question is 62 over 15, which is also the same as the manually calculated one.
Question 3. For question 3a, we needed to find the surface area of a paraboloid cut off by the plane z equal to 1. We started with the standard surface area formula involving partial derivative. Differentiating z equal to x squared plus y squared gives us 2x and 2y. Substituting this into the formula, we get the square root of 1 plus 4x squared plus 4y squared. Then we factor this to 1 plus 4 bracket x squared plus y squared bracket. Since the region of integration is a disk where z equal to 1, we again switch to polar coordinates. The term x squared plus y squared become r squared, the limit of r from 0 to 1 and theta from 0 to 2 pi. We use u substitution with u equal to 1 plus 4r squared. We solve the definite integral. This yields the exact solution of pi over 6 bracket 5 square root 5 minus 1 bracket, which is approximately 5.33 units square.
For question 3, our first step is to declare the variables that we need to use for this question, which is x, y, r, and theta. The next step is to define our z equation, and then after that we need to do the partial derivative for dz dx and dz dy. After that we need to define the area at the formula for the surface area, and then before we do the calculation we need to change it to the polar form so that it can be calculated more easily. And x and y is replaced with r cos theta and r sin theta, and then the whole equation is multiplied by r. After that we do the double integration, and the inner part of the integration is for the dr. The lower limit is 0, upper limit is 1, and for the outer part is for the theta. The lower limit is 0, the upper limit is 2 pi. And then we display the answer, and it is also same with the manually calculated answer.
Question 4. For question 4, our aim is to find the volume of the solid G using the triple integrals. This solid is bounded by the slanted plane y plus x equals to 1, the parabolic cylinder y equals to x squared, and the floor z equals to 0. The most important step here is choosing the correct limits of the integrations. Looking at the geometry, the height of the solid, or we can say the z limits, range from 0 up to the plane 1 minus y. The y limits also extend from the parabola x squared to the line y equals to 1. Thus, the x limits falls between -1 to 1. Besides, after setting this limitation, we set up the integral in order dz, then dy, then dx. We first integrate the constant 1 with respect to z to get the height 1 minus y, and then integrate the result with respect to y. When we reach the final outer integral with respect to x, we can get the resulting function is even. This allows us to integrate from 0 to 1 and simply multiply the result by 2. After finishing the calculation and simplifying the fractions, we get that the total volume answer of the solid is 8 over 15.
So for the last question, question 4, the first step is to define all the variables that we need to use, which is x, y, and z. So we know that to calculate the volume, we need to do it from inside to outside, which is from z and then y and then x. So the first part we need to do is we need to integrate with respect to z. So from the equation here, we can see int1 is the equation, and then z is the we with respect to z. The lower limit is 0, the upper limit is 1 minus y. And after that, we do it for the dy, which is with respect to y. We just int the we just integrate the dz. The lower limit is x squared, the upper limit is 1. And then the volume is equals to the integration of x also. So from here, we just integrate the dy with respect to x. The lower limit is -1, the upper limit is 1. After that, we just display the answer, and the result we get from this software solution is at over 15, which is also same with the manually calculated one. So that is pretty much all from us group 9. Thank you for your attention.